we have this observation that the average flux control coefficient was higher near the beginning of the pathway than near the end. So we'll do some plots in a minute.
Could you zoom in?
Can I zoom in? No. Are you seeing the Python screen?
Yeah. It's a little small.
It is. Yeah. Okay.
We can control plus or something.
Yeah. Hold on then. I didn't want to do that. Let me do this. Plot show. Well, I think what I have to do is increase the font size. I think let's try that.
Oh, this block would look cool.
Yeah, it's two bar graphs on top of each other. Let's see, where appearance. Yeah, this is it. See if that'll make it bigger. Yeah, this version has a little problem, I noticed, for changing the font size. I reported it, but they couldn't find any problem. So sort of frozen. Yeah, see, not responding.
Or you couldn't do control plus?
No, I just wanted to increase the font size. I think it's increased now, though.
Oh.
This hopefully hasn't forgotten all the tabs. Okay, so it's slightly bigger. It sorts itself out.
Yep.
So if I run this, okay. We guess it'll come up there, yeah, the first one. So yeah, so we have this unusual observation that most of the sensitivity is in the first step, and then it declines pretty quickly as you go from step to step. So the x-axis is the step number, so that's the first step, and the number 10 is the last step, and the y-axis is the sensitivity value. This is what happens if you now add negative feedback from the last step to the first step. Basically, there's hardly any sensitivity in the middle, and it's all concentrated mainly on the last step and some on the first step.
So why is it have so much in the last step? Like,
okay, let me switch to. It's actually quite easy to understand that. This one is easy to understand. Is easier to understand than this top one. So let me. Oops. Let's go. Yeah. So let me de-share that. And we'll do this. Did I share it? Apparently not.
no.
The plugin is required. What? A plugin is required to share. Oh, install. Okay. Oh, they must have updated it or something. Okay. Okay, here we go. Okay, so if you have, so we have something like this. So let's just put 3 steps in, okay? This is fixed. We have a feedback going back to here, all right? So that's negative feedback, all right? So it's actually really easy to explain why most of the sensitivity is here on the last step. If I were to increase, let's say I increased this one, all right? So if I increase this, you'll agree that this goes up? Yeah?
Yeah.
And if this goes up, of course, this goes up, and then it represses it. So this comes down, and it basically neutralizes my initial increase. So this explains why these middle steps don't have any sensitivity at all, because the negative feedback cancels out any effect that you make. If we go to this step here, let's do a different color. If I increase this, okay, what happens? The rate goes up, that pulls S2 down, okay, because it's using it up faster. So if S2 gets pulled down, the negative feedback decreases. So negative feedback decreases, there's less inhibition. So this goes up. Therefore, this goes up. Therefore, this goes up. Therefore, pushes this back up. So if I increase it at this point, what the negative feedback does is it stabilizes S2. Okay, so S2 is robust. Well, let's just what word shall we use? Is resistant to changes in, let's call this 1, 2, 3 V3. Right, so it's S2 won't change much at all. So it's acting as if it were its own little pathway, because S2 looks fixed to V3. So if I increase V3, the negative feedback responds by maintaining S2 relatively constant. Okay, now you can see this effect with a two-step pathway, actually, graphically. If I had a two-step pathway like this, okay, V1, V2, right? And I'll make this a simple mass action, okay? And what I'll do is I'll plot V1 and V2 against S1, okay? If I plot V2, it's a straight line, okay? I just get that, right? Now, what about V1? Well, why don't I give V1 a negative feedback? Now, negative feedback is actually an inverted S, right? So an S looks like that. So an inverted S is like that. So I'll draw that. Right, so this is V2, this is V1. And you'll notice here that this point here, that's the steady state point. That's where V1 equals V2, okay? So that's the steady state level of S1, right? Now, what's the equivalent to changing the V3? The equivalent to changing this V3 up here is the same as increasing K1. Increasing K1 is the same as changing the slope of this line. Okay, so I can change K1, no, K2. If I change to K2, this one here, K2 here, actually that should be a 2, shouldn't it? K2, the line just swings up and down. And you notice that as the line swings up and down, the change in the steady state concentration it changes in a fairly narrow band. And it's a narrow band because this line here is so steep. Okay. And the steepness of that line is dependent on how strong the negative feedback is. So if I were to do a similar one, but make it, let's say I have very strong negative feedback. Let's do some really strong negative feedback. It will look like very strong negative feedback is almost, a vertical line. And now if I put my line through it and I swing it about a bit. So if I change the K2, you can see that the S hasn't changed at all. So this is S1 and there's V1, V2 again. So when this slope is really, really steep, which is when you have very, very strong negative feedback, the change in S, the S1 changes hardly at all. So it's very robust changes in V2. So as I said, it's as if this piece here were its own pathway now, because V3 sees S2 as essentially fixed. Okay, and so I get full control at that point.
Which of that?
This piece here, I have full control here over the flux
Yeah.
because S2 is pretty much almost fixed because of this property here. And so and from the point of view of V3, it looks like it's its own little single step pathway. Because when you increase V3, S2 doesn't decline. Maybe I should explain something actually here. Maybe I should explain something which might make things make more sense. So
you should plot the x-axis is S2.
But on this one, yeah, but I wanted to reduce it to two-step. With a two-step, I can do it with a single 2D plot because I've only got 2 rates, whereas here I got 3 rates. So let me explain this. Perhaps this is something I didn't really explain. So I got 2 coefficients here, okay? EJ, E1, EJ, E2. What determines their magnitude? Whether they're close to 1 or close to 0 or halfway in between. I mean, this could be 1.5 or 0 or any number in between, right? What determines this number? Okay, so let's extract this here. Fix this, okay? So I got V1 here, fix this, right? What would be the control coefficient on this single step? So there's a fixed thing here as well, okay, by the way. So let's say that V1 is E1 times, I'll make that X0 over Km plus X0. So that's just a Michaelis-Menten equation, all right? Okay. The steady state flux. So the steady state flux equals V1 actually, because X0 is fixed, okay? And E1 is the thing I can change up and down, right? So in order to get the control coefficient, all I have to do is differentiate this with respect to E1. So Cj, in this case, Cj is just V1 dE1, E1 over V1, right? I can do that because V1 in this case is the flux because both the reactant and the product are fixed, right? So if I differentiate this, right, so differentiate this one here with respect to E1, I get X0 over Km plus X0 times E1 divided by V1. Well, V1 is this expression here, so I'll divide it by it. So it's Km plus X0 divided by X0. Cancel, 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 cancel. Oh, there's an E1 here as well. E1, cancel, cancel. So I get 1. So the control coefficient for a single reaction, right, with fixed reactant and product is 1. Right, that's the maximum amount of sensitivity you can get from a single reaction, all right? So this system up here, all right, which is only 2 steps, for a two-step pathway, the maximum can be 1 and the smallest can be 0. So it goes from 0 to 1. So what makes the control coefficient less than 1, right? What makes it less than 1? Okay, let's do a thought experiment. So now let's take this step, right? This single step, and I'll hook it into 2 steps, all right? So this one now floats. This floats. Okay, it floats, all right? All right. So if I increase this, let's do it in red, I guess. So let's increase this, right? What happens next? S1 goes up because it gets made faster. If S1 goes up, this goes up. So the whole rate through the pathway goes up. So let's write down the conclusion here. So J goes up, S1 goes up. Okay. Do you agree with those two?
Wait, here, what is J? Like,
Yeah.
what does J mean?
Yeah, so I'm gonna call J is the rate V1 or V2. I can pick either one because they're the same as steady state. So this equals J, okay?
Yep.
They are steady state, they all each other. So if I make a delta, let's do a delta E1. So delta means change. If I make a delta E1 change, what happens to the flux? The flux goes up by an amount delta J, right?
Yeah.
You saw that. The other thing that happens if I do a delta E1 change, the S1 goes up too. See, S1 goes up. You're supposed to, do you agree with those two statements?
Yeah.
We don't know how much they go up by, but they go up. Okay, all right. Now, so S1 has gone up. What does that do to the reaction rate through E1? Okay, so just redraw it down here. Let's go back to the, so this is what we had, right? And I increased that and this went up. What does that change in S1 do to the rate V1?
Oh.
Go up as well.
Hmm?
Would it go up as well?
Well, let's do some basic kinetics, shall we? So let's have a reaction, substrate, product, reaction rate. If I increase the amount of substrate, oops.
Oh, I see.
Well, if I increase the amount of substrate, what happens to V?
Go up.
Goes up.
More.
If I increase the amount of product, what happens to the forward rate V?
It's slower.
What?
Down.
Goes down.
Go down.
Yes, goes down. All right. So because S1 here has gone up, it's now going to squeeze down V1 a bit. Do you agree with that?
Yep.
Yes. So in fact, although originally I thought I was going to get a nice big increase in the rate because I increased E1, that is going to be slightly reduced by the fact that S1 increases and inhibits its own production.
Wait, is this same even in irreversible reactions?
Oh yeah, I don't. No, it's different. No, totally different.
Okay.
Yeah, sorry. Yeah, this is reversible.
Okay.
These are reversible. Okay. Yeah, yeah. I'll come back to the irreversible one in a minute. That's the irreversible one is actually the trivial situation. So what's happening here is that I guess let's go through the sequence, shall we? So delta E1 goes up. This results in delta S1 going up. Actually, this also results in delta J going up. All right, but the delta S1 going up results in delta J going back down again. Okay.
Yeah.
Now this is less than this one though. So it still goes up a bit, but not as much as you thought it would. That's why the control coefficient is always less than 1.
I see.
If I look at the case, the irreversible case, if I increase E1 here, this goes up, but because it's irreversible, nothing happens. And so I get the full impact of a delta E1 change.
Mm-hmm.
So in this case, actually, the control coefficient here is 1. And in fact, by the summation theorem, the control coefficient here is 0. In fact, this makes complete sense. If I increase this, right, that goes down, right?
Yes.
Consumed more, right? But because this is irreversible, this step doesn't notice a thing. It is unaffected. Therefore, the flux remains the same. The flux is unaffected by changes in E2.
Oh, I see.
Yeah.
Hmm.
So yeah.
Oh wait, I thought like if you increase E2, then S1 go down.
It does.
Then it doesn't inform the. Oh,
Yeah.
I see, because the race is depend on S0 or something.
This is the irreversible case.
Okay,
This is the reversible case.
I see.
It's reversible in V1, okay? In the irreversible case, what it means that any perturbations downstream don't get transmitted upstream.
Right.
There's a block. There's a blockage at the irreversible step, okay?
Yep.
Whereas with the reversible step, you know, perturbations can flow up and down the pathway, whatever they want. And so in this case here, you get a slight inhibition by S1 because it goes up. And that slight inhibition then reduces the full effect of E1. If you had a full effect on E1, you'd get a control coefficient of 1. But we don't get the full effect. So what ends up happening is that CJE1 is less than 1. In this case, you don't get the full effect. All right. That also means then, by the summation theorem, some of it must then end up in the second step. You think of it as, I sometimes think of it as a sort of a, you know, a sausage balloon. You know, these balloons with like a shape of a sausage. You squeeze one end, the air goes from there to the other end of the balloon, and the balloon blows up. So there's a sort of finite amount of air in this pathway, and if you squeeze one end, it appears somewhere else. So if this control coefficient goes down, it has to reappear somewhere else. So that the summation must always be 1.
So that's for the reversible case.
Oh, it happens in irreversible as well. Look, oops, sorry. Look, 1 plus 0 is 1.
Yeah. Yeah, but like when the coefficients of J with respect to E1 less than 1, is it when it's have a branch or something?
No, it's this case. It's this case, yeah.
Oh, that case there you have 1 reversible, right?
Yeah, this is the reversible case.
Okay.
It's less than 1
I see.
because S2 reduces the full impact of the delta E1 change.
Right.
If you only have the delta E1 change, you get a control coefficient of 1. But in this case, in the reversible case, delta E1 also causes S1 to rise. Because S1 rises, it pushes back on V1 and slows it down a little bit. You still get an increase, but not as much as you would have. All right. Now, the strength of this effect, the strength of this, well, this is basically a feedback, actually. It is actually a feedback mechanism. The strength of this feedback, in other words, the steepness of this slope, right, that's basically what we're talking about, is governed by something called the, elasticities. Right, and they're given the symbol epsilon. It's usually epsilon Vs. This is the strength at which a substrate or a product affects its immediate environment. So let me first of all define what that is. Epsilon Vs is the partial derivative, or whatever your rate law is. That's just a derivative, then scaled. Okay. So if I were to plot V against S, right? Let's say I plotted V against S, and I get a sort of hyperbolic curve like that. So I got, you know, S going to somewhere. I don't care where it goes to. I got a V there, and I did an experiment where I plotted V against S. I get a shape like that. Okay, if it's an enzyme. If I take a particular point on S, that slope there at that point is the is the dV by ds. It's this thing here. Okay, that's just the slope, right? So the elasticity is the slope of the reaction curve, i.e. this thing, because this is just V against S. So it's the slope, right? But it's the slope that's been scaled by S over V, just like the control coefficient, all right? Now for an enzyme mechanism like this, that looks like that, if I plotted the elasticity at the same time, it actually starts out of a value 1 and then just drops down to 0. So this is the elasticity, okay? That's the scaled one. So it starts off 1, and that basically starts off 1 and then falls down to around about 0. All right.
Mm.
Now, if I look at this, look at the elasticity for a really simple reaction. Let's say this one where V equals Ks. Maybe you can work this out for yourselves. Work out the elasticity for Vs, V epsilon Vs. So what you have to do here is you have to work out the derivative, and then you multiply by S and divide by V. Okay, see if you can do that.
Oh, okay.
S squared V.
What? This is calculus 101 or 99. It's even less than 101.
So can you draw up when you calculate the derivative of
So calculate dV by ds first. What's that?
N?
Let's see. So it's kind of constant.
It's K,
Oh, sorry.
right?
KSV divided.
Just K. Yeah, now you go K, now you do the S divided by V, but I know V is KS.
Oh, I see.
So it actually equals 1. So for a first order mass action kinetic reaction, the elasticity is 1. And it basically corresponds to the case when the reaction is linear. Is a linear function of S. All right. If here's another one. If V is Ks squared, right? dV by ds is 2Ks. Okay. Then I'll multiply by S divide by V. So multiply by S divide by V, and V is Ks squared. Cancel, cancel equals 2. All right. So the elasticity is obviously closely related to the what's called the kinetic order of the reaction. There's first order, second order, third order, 0 order. What we have with an enzyme, though, we have a variable order case. So the elasticity can vary in value from 1 to 0. Okay. Now at the 1 point here, it's 1 because down here, it's acting almost like a mass action, simple mass action reaction. Okay. All right. Up here, it's acting as a 0 order reaction, and so the elasticity is 0. So let's say we had that. What's the elasticity of that? Where dV by ds is 0. So the elasticity is 0. So when the slope is horizontal, the elasticity is 0. When the slope is down here, when it's linear, it's 1. And then you go from 1 all the way to 0. Somewhere around here, it's 0.5 or something, passes the 0.5. So the strength then, the strength that a substrate has on a reaction is governed by this elasticity. These are pretty important things, actually. They tell you how much influence a substrate or a product or anything else you're interested in has on the reaction rate. Okay. All right. So let's do some little exercises, shall we? Let's do.
I have one question on this.
Yeah.
Well, would you scroll up when you do the control coefficient J with respect to E1?
Is it this one?
Way up, one more. Yeah, this one.
Yeah.
Yeah, so multiply E1 divided by E1. Oh, that's the scale, right?
Yeah, that's I scaled it down here. Here's the scaling here. Oops. This is the scaling here. Where is it? Sorry, there it is. That's the scaling. That's one scaling, and that's the other, and that's the other scaling. So yeah, so here I differentiate with respect to E1. Right.
And this is only irreversible, right? Just go straight.
This is just for a single pathway, single step.
Oh.
That was a single step. I just wanted to show you what the control coefficient was for a single
Well,
step.
no, but like this one, you zoom in from that single step.
Oh yeah, well I took it out. I removed it, and then I fixed x0 and I fixed s1. So
Okay.
maybe we can summarize actually here.
Okay.
So single step.
Yes.
Okay. So there's a single step, right? With a single enzyme. There's only one control coefficient, and it's 1. Has to be to satisfy the summation theorem anyway. Right, it's 1. For 2 steps, I can't tell you what the values will be, but I know each one will be less than or equal to 1 or greater than or equal to 0. Okay, but I can't tell you what value it'll actually have unless I do some more investigation. Right, but for a single step, it's always 1. For 2 steps, each one will be greater than or less than 1. But the summation is always 1. Okay. All right. So let me just show you some of these ideas then by doing a quick simulation. All right.
Yep.
So let's go to here. Okay, let's go. So I've got a fresh thing there, right?
Yep.
So I'll do. Oops. I don't care about the where it goes to, so I'm just going to leave it out. Okay. So let's do. I'm going to put a full. Okay, one thing I need to remind you: the Vmax equals E. So Vmax 1 is E1 times the K cat. Okay. So when I put a V1, there's actually E1 in there, right? That's where the E1 comes from. X, I need to do a full reversible one, okay, for this. Let me do a full reversible one here. Oops, hold on, sorry, what am I doing? X0 minus S1 divided by KX, and I'll do 1 plus X0 divided by K1 plus, this is just a full reversible Michaelis-Menten rate law, okay? This one here, I'm just going to have a simple mass action. Okay, so let's set these up. I'll just set these to 0.5. We'll mess with these a little bit later. X0 equals 1, K2 equals 0.1. Let's see what that does. Maybe I've missed out the equilibrium constant. Equals 2. There you go. Let's see what we get. Oh, I missed out. Oh, yes, 2. Okay, good.
A2.
Okay, that's what I'm getting. Oops, I forgot to fix this. That's better. There you go. Let's put some limits in on the y so it doesn't look so weird. 0 to 2. So I'm just setting the y-axis. I just set it a bit more. There you go. Yeah, reach a steady state. Okay. All right.
Okay.
Good. Okay, I'll compute the steady state to make sure we're at it. All right. There you go. Okay, let's compute the control coefficient, shall we? Print. So this is going to be the first one, C1. R get CC. I need to put the fluxes in. Let's call it J1. I'll copy this to the chat in a second. VM1. Let's copy this to the chat to get you started. Yeah, it's in chat. And I'll print the other one.
The VM1 is that the E1?
That's the Vmax.
Yeah, but you couldn't do like J1 E1.
I could, yeah.
Okay.
Hold on. What do you mean J1 E1?
like according to the.
I mean, I could do this,
Oh, I see.
and I can put E1 there,
Yeah.
right?
But you have to put k cat.
Yeah, but then I have to put k cat in, and I'll set E1 to 1, and I'll say k cat to 5 or something. This might mess up things a bit. K cat. It was 10 before, wasn't it? Let me make it the same, all right? Okay, that's the same, it's better. Okay, so the other thing I've done is I've also printing out, let me give you the copy of this then.
Yep.
There it goes. So so that's the control coefficient for the first step. This is the control coefficient for the second step. I'm using K1, right? Because that's sort of equivalent to E2. If you want, I could put E2 there if you want, just to make it clear. E2 equals 1, and then I can go E2 here if you want. Okay.
Yes.
And here are the two control coefficients. Let me just put a print there to spread it out a bit. There they are, 0.89, 0.91.
It's really satisfying to see actually they are one.
See what? So
The
to see
sum
that
is one.
they sum to 1, yes. Yeah, right, yeah. Phew. That's right, we sum to 1. So the question is, why has CE1 got so little control over the flux? If I drew this out, I mean, what? Yeah, why would E1 be so small? CE1 be so small? What's making it so small, do you think?
Is it the feedback you're dividing some?
I mean, there is feedback here effectively because S1 here, if I increase S1, it slows the reaction down. Yeah, okay, and here as well. So S1 is like a product, it's inhibiting the reaction, all right? So why do you think it's so low? Why do you think it's so low though?
Maybe kcat is really high. That's why.
Maybe, but that's not the answer I'm looking for.
Um,
Think in terms of elasticities. Do you think elasticity is big or small on S1, J1? In order for this to be so low, what has to happen in the pathway when you make the perturbation? All right, let me go back to the let me draw this instead then.
So it's have to be steep, right?
Yeah, that's right. It has to be steep. Yeah, so what I've got here, I've got a reaction here, right? And for some reason, this value here is only 0.08. So operationally, what's happening is I'm increasing E1, okay, which then decreases S2. But the fact that this is so low must mean that S1 is having a really marked effect on the reaction rate through E1. So S1 must be a very strong inhibitor. Yeah, even a small increase in S1 slows this reaction down a lot, so that we only get a change of 0.08.
No, but like this one is non-reversible. So how could S1?
No, this is reversible.
Oh, okay.
And the one in the example is reversible. Both reversible. So my prediction is that this elasticity here is big. But of course, I have to admit, there's one other thing about it, though. It is big. Well, first of all, I have to say, is it positive or negative?
Wait, it's negative, I think? Or
So,
slow down.
Yeah, so it must be negative. So first of all, it's negative.
Yeah.
Yep.
Is it very negative? Yeah, my prediction is that it's very negative. To have such a profound effect on the flux. Okay, so let's go back to the simulation. So what I need to do then is to ask it for the elasticity, right?
Yeah.
So let's do that. The elasticity of S1. And the reaction rate, the reaction I'm looking for is J1. And the substrate or the species is S1. Here we go. Ta-da!
I see.
That's big. It's negative,
The J1 is back.
and it's very negative. It's very negative. Yeah, it's very negative, basically. Very negative.
Wait,
okay?
you. Let's see. Let's see.
So that's the elasticity of S1 onto V1, onto J1, onto the first one, right? So that means a 1% increase in S1, a 1% increase in S1 will cause a 10% decrease in V1. Do you see? It really clamps down on V1, and that's why the sensitivity is so low. So how can I reverse this? Well, the way to reverse this is actually somehow to make this much closer to 0. All right, so I'm gonna have to figure out how to make this much closer to 0.
I have a question.
Yeah.
So when you say control coefficient J with respect to E, like say E1, if it equal 1, then it fully like be affected by E1.
Yeah. Yes, fully affected by E1. Yeah.
So in this case, like if it equal, if it here it's close to 0.
Yes.
So
Hardly
so
any
we
effect.
have
Hardly any effect.
right.
Very little.
Right,
So-
but like, why did you say like this one E1 affect a like J1 a lots in the control coefficient
S-
is
well-
low?
So S1 is having a large negative effect on J1.
Not E1,
Well, J1 and V1 are the same thing at steady state.
not E1.
Not
Right.
what?
Not
Yeah,
E1.
not E1.
Okay, I
E1
see, I see.
has very little effect. And
Okay,
it
I see, I
has
see.
very little effect because the reverse elasticity is so strong.
Okay, I see. Yeah, it's just
Yeah.
the
No.
term.
This is most people, I tell you, vast majority of people don't know this. They don't know why some steps are more sensitive and less sensitive than others because they don't think of this in terms of a system. This is a genuine system property. All right. These control coefficients are a result of the system acting as one thing working together to produce this number. I cannot tell you this number just by looking at one step. It's actually a concerted effect of all the steps operating together. Okay, how can I increase this? Well, one way to increase is to reduce the effect of S1.
Decrease K-cat.
Increase K-cat. Okay, we'll increase K-cat
I
to 20.
mean decrease.
Decrease K-cat to 2. Oh, it did.
Yay!
Oh yeah.
No, I think what's happening there is because the K-cat is lower, the steady state level of S1 is lower.
Oh, so that's why.
And I think maybe it has less of an effect then. Like,
Oh, that makes sense.
this is, let me see. What happens what happens if I increased a K2,
Mhm.
say 10 times more? That will decrease S1, all right? Similar thing. I think it's something like that that's going on, all right? So in fact, I could push it up even more, I guess, see if I can get this rate down a lot.
Low.
Yeah.
Yeah. So now the first step is getting more and more control. The second step is losing it. It has to lose it because of the Flux Summation Theorem. So you get this, this balloon effect, this sausage balloon. It goes back and forth, depending on the properties of the individual enzymes. Okay. So
Wait, so if you decrease K-cat, it means the enzyme
slower.
be more effective, right?
No, it's slower. It's a multiplier. So if you reduce
I see.
K-cat, it slows down.
No, but but why in this case the control coefficient be more effective by E1?
Because the elasticity has dropped. So S1 has less influence now on V1 than it did before.
Interesting.
Right? It has
Well,
less effect. It has less effect,
I
so
see.
you're getting more of the effect from E1. So it's a
I
balance
see.
between, there's a balance here, right? E1 wants to increase the flux. S1 decreases the flux. So you have this
Right.
balance between the two. If S1 is not very effective, then you get the full effect from E1. If S2 is very effective at inhibiting V1, then it'll neutralize any effect E1 has. All right. In fact, I mean, if I push this up, to 50, let's say, 0.02, it's gone minus 45 now. No?
Right.
So S1 is very potent, has a very potent effect on V1. All right. So
Wait, but like, what's the connection between K-cat and S1?
the connection is if I increase
Like,
K-cat, if I
you
increase
have
K-cat,
more.
I'm increasing the flow, and therefore
Yeah.
S1 goes up.
Yeah.
If I decrease the K-cat, I'm reducing the flow, and therefore S1 goes down.
Right.
But everything is transmitted through S1.
Right.
S1 is the key transmission point. All perturbations are transmitted then through S1. And S1 has this effect on either V2 or V1 or V2. And you can imagine this gets more and more complicated as you get longer and longer pathways.
Yeah.
So, okay. I think that's probably enough for that. I think I'm not going to go any further on this, but we'll revisit this idea and continue talking about this next Tuesday, because ultimately I want to go back to why on earth do we get this pattern? Okay.
Yep.
Well,
that's all to do with elasticity. That pattern is.
So what I'm guessing, like, even if you get a large enough like randomized data set, then my feeling is it's gonna add up to 1, right? Like,
no, but there seems to be a bias
right.
though towards the front steps.
Yeah, that's
there's a bias towards the front steps, which seem to have more control than the steps further down the chain.
I see.
There are a number of levels you can explain this on. There's a really, really simple. When you get to the bottom of it, it's actually pretty simple, but it takes a bit of digging before you get to that point.
Right.
So this is one reason I find these kinds of analysis useful, because they force you to think about what's going on.
Right.
They force you to think about in a step-by-step manner. This goes up, therefore this goes up, therefore this goes up, and the strength of this matters. That goes, and and then eventually you realize how the thing works. So it's better than doing you can do simulations all day long, and you still won't understand how it works. But you can sort of dismantle